to tell you a little bit about the so-called Riemann hypothesis. And the subtitle of the talk is How to Make $1 Million Without Getting Out of Bed. So let me explain why that's the subtitle. Let's go in reverse order. So why don't you need to get out of bed to study this problem? In the other sciences, physics, chemistry, biology, what you need to do is observe the physical world, the real world that we live in. And you need to say, whatever it is that you're studying, you will want to make, you observe the world and make a mathematical model, a sort of, let's boil everything down to the bare essentials. So this is a very crude approximation of what's really going on. You solve the model, and once you do that, you hope that it's going to predict real-life behavior. So here's a very important example of physics in action. You need to make sure that the angry bird will knock the pig over and then tumble the whole castle. Okay, so this is how physics would approach the problem. In mathematics, on the other hand, of course you're influenced by the outside world, but you don't need anything other than your mind to think about numbers. And concepts coming out of mathematics work just the same halfway around the world in India or China or on the moon, as far as we know. And even 2 plus 2 is still 4 when you get to the moon, or Mars, or in your bed. So that's the reason that you can do this. You can think about this problem without going anywhere. Of course, it helps maybe to go to finish high school, college, grad school, and so on. One of the drawbacks is, if we're just playing games in our mind, we have to completely convince ourselves that we know what's going on. With Angry Birds, if you tell me shoot at 45-degree angles and I swear it's going to hit the pig, well, all I have to do is actually shoot it. And then we know who's right. And in math, we're going to have an argument, a proof. Another word for proof is argument. So you have to have a completely sound explanation for why you think what's going on is really what's going on. All right. Let me tell you about this, the second part of the sentence, $1 million prize. So in the year 1900, this is 112 years ago, there was a big famous meeting, international meeting, mathematicians from all over the world came together. And one of the most famous of these mathematicians is a guy named David Hilbert. There he is with a hat. And what he suggested is he proposed, these are problems that were around, at least some of them, but he sort of collected them into, here are the most important problems. There are 23 of them. 23 of the most important problems for mathematics to tackle in the next 100 years. Here are the problems for the 20th century. And number 8 on his list are Riemann hypothesis. Fast forward 100 years, the year 2000, not so long ago. Some of you were born then, by then. There's a new Clay Maths Institute that was just founded a year before, and it was based at Harvard. Now it's based at Oxford. And they posed not 23, but 7 problems. 7 problems for the millennium. The millennium problems, prize problems. Not only did they pose them, again, these are problems that were well known. They didn't pose them, they just collected them and said, these are the most important. They put a $1 million bounty on each problem. You solve even one of these problems, they will give you $1 million in cash. And number 4 on their list is the Riemann hypothesis. In fact, it's the only problem which appears both on the most wanted list in 1900 and the most wanted list in 2000. So this thing is really one of the most important problems in all of mathematics. In case you get so discouraged, oh, there's not a chance, there's no way I'm going to be able to solve this thing. People have been thinking about it for 150 years. Number 3 on this list, on the Clay Math Institute $1 million list, is the so-called Poincare conjecture, which we will not discuss today. You may have heard, you may have watched math news, probably you don't. 3 years after this problem made its most wanted list, the Millennium Most Wanted list, a guy named Grigori Perelman solved the Poincare conjecture. So it's not impossible for these absolutely unbelievable problems to get solved. I should say he had been working on it much longer than the 3 years between when it became a prize problem and when he solved it. And it's based on 100 years worth of mathematics. And I should also tell you that when they gave him the $1 million, he said, "Thanks, but no thanks." And that's him kicking the $1 million away. The proof was enough for him. Just the satisfaction of having proved this thing was all he wanted. So the caveat is, okay, this problem's hard. If you solve it, fantastic. You'll be world famous. But if there's a tradition of not taking the million, you might have some pressure not to do it. Take it anyway. It's $1 million. Why not? All right. So what is the Riemann hypothesis? Well, it was stated in 1859, over 150 years ago, by Bernard Riemann. There he is again. And it's seen hundreds, if not thousands, of false proofs. People that write papers, even publish papers, circulate papers, professional mathematicians, amateurs, experts in the field, have given false arguments. Arguments that when they showed to someone else, they said, wait a second, how do you get from this line to this line? A miracle occurs. Well, that's not an explanation. So it's seen hundreds of false proofs, and whatever it is, I'll try to explain what it is. Numerically, it's been verified 1 billion times. It's really predicting what's supposed to happen. We just don't know why. Okay, so let's not beat around the bush. What is it? What is the Riemann hypothesis? Well, it's complicated. If it wasn't complicated, it wouldn't be such a hard problem. But I'll give you the one-sentence version. It's that Riemann was the first human being to hear the music of the primes. And my hope is today you will too. All right. So, the Riemann hypothesis is a problem about prime numbers. So let's talk for a second about prime numbers. Just to get a warm-up, what are the divisors of 6? What are the whole numbers that evenly divide 6? Please, sir.
1, 2, and 3.
1, 2, and 3 are divisors. We'll also count 6. So 6 is its own, any number divides itself evenly. Any whole number that divides evenly is called a divisor. Thank you very much. That's a perfect answer. 1, 2, 3, and 6 are the divisors of 6. Now, what is a prime number? Yes?
A number that can't be divided by anything but itself and 1.
Perfect. And so, it has exactly 2 divisors. Because it can only be divided by 1, and it can be divided by itself and no other number. Yes, sir?
Is 1 considered a prime number?
Excellent question. At the time the Riemann hypothesis was posed, 1 was no longer considered a prime number. But for a long, long time before then, 1 was considered a prime number. So today, for very many reasons, we do not consider 1 a prime number. So 1 does not count, and that's exactly why I say exactly 2 divisors. 1 has only 1 divisor itself. Okay, excellent question. So you probably have seen the primes. Here's a short list of some of them. 2, 3, 5, 7, 11. You can read.
2 is the oddest prime.
I'm sorry?
2 is the oddest prime.
2 is not a prime?
2 is the oddest prime.
2 is the oddest prime. Absolutely. Absolutely. Yeah. 2 is, absolutely. 2 is the weirdest of all the primes. It's the only even one. It has a lot of very strange properties, but it is a prime, whereas 1 we will not consider a prime, at least today. Why are these things important? Why do we care about prime numbers at all? What makes them any different from 6? The primes are the building blocks of all numbers. If you take any number, you can decompose it into primes. Maybe it's already a prime. And in that way, they are like the elementary particles in physics, the indecomposable pieces of matter and our universe that make up everything that we know. So any number that we know of can be decomposed into primes, and that's why the primes are so important. They're the fundamental building blocks. So you can think of 2 as an electron, 3 as a lepton or photon, 101 Dalmatians for some reason, or Higgs boson if you know what these things are. Okay. Now, in the standard model, there are 12 fundamental particles, and that can change from time to time. So this is another reason why mathematics is different from sciences that observe the world. Newton knew exactly how physics works until Einstein changed it, and now Einstein knew exactly how physics works until quantum mechanics changed it, and so on. So these things change with time. Primes, except for 1 changes whether we consider 1 word. The facts about numbers do not change throughout time. Okay? They're absolutely universal. So there are 12 fundamental particles. How many primes are there? How many people think there are 20 prime numbers? Raise your hand. More than 20. That's right. You should be upset. How about 30 or 100 or 1,000 or 1,000,000? How many primes do you think there are? Let me pick on some. We all know the answer, right? Infinity, right. There have to be, right? Because we can make a computer program and just keep looking for them as far out as we want. But that's not a proof. That's an observation. That's not a proof. We need a rigorous argument. We need a very, it's not something that you just, it has to be. You can't just throw your hands up in the air. That's not a mathematical proof. So today we'll prove a theorem. Our first theorem of the day. There are, in fact, infinitely many prime numbers. The proof that we're going to present, there are many, many proofs of this fact, but the earliest proof that we know of is by an ancient Greek mathematician named Euclid, who lived in Alexandria, modern Egypt. And it was given 2,300 years ago. Pretty amazing. The first thing we need to know to present Euclid's proof is, what does it mean not to be prime? So a number is composite if it's not prime. What does it mean for a number to be composite? How do we tell that n is composite? Well, like you said, we just check if some other number divides it, and it's enough to check if some prime divides it evenly. So a number is evenly divisible if it leaves a remainder 0. So we're going to check if 75 is a prime or not. Well, we try to divide it by 2. That leaves a remainder of 1. So that doesn't tell you anything. But if you divide it by 3, it leaves a remainder of 0. And so if a number has a remainder 0 when divided by some prime, then it's not prime. Then it's composite. Right? That's all we need to know for this proof. So how does the proof go? It goes by contradiction. Let's say I'm wrong. Let's say we're all wrong. And there are only finitely many primes. Okay? If we can find a contradiction to this assumption, we'll just follow very logically from this assumption and come to something that just doesn't make any sense, then this assumption must be wrong. And there have to be infinitely many primes. So this is what's called a proof by contradiction. So let's assume, for now, suspend your disbelief, let's assume that there are only finitely many prime numbers. Let's list all of them. There's only finitely many. 2, 3, 5, 7, 11, 13, on and on. 100 million, a billion, a jillion, a googolplex, however many there are. There's some largest number, which is prime, which is capital P. So now we have this list of every prime number in the universe, and it's a finite list because we assumed it is. Take this number, capital N, where you multiply all the primes by each other. So 2 times 3 times 5 times 7, all the way up to this hypothetical largest prime ever, capital P. You multiply all these together, it's a finite product of finite numbers. N is just some integer. Take this integer and add 1 to it. Okay, so N is the product of all prime numbers with one more tacked on the end. So let's test whether or not N can be prime. Well, or let's test if it can be composite. So if you take N and you divide it by 2, well, this piece is divisible by 2. So what remainder does it leave? 1. If you take N and you divide it by 3, it leaves a remainder of 1. If you were to take N divided by 57, it's not prime, 59, it leaves a remainder of 1, right? So any prime number, since all the prime numbers are here, when you divide N by any prime number at all, it leaves a remainder of 1. And 1, last I checked, is not 0. And so, this number can't be composite because if it left a remainder of 0 when divided by some prime number, that's what it would mean to be composite. So that means N, this big number N that we wrote down, is not a composite number. Well, what does that mean by definition? If it's not composite, then it's prime. Right? What's the problem with that? Anybody else? I already picked on you. Yes, back there?
I thought that P was the highest prime number.
Perfect. P is the highest prime number, and yet we just showed that there's another number which is prime, which is bigger than P. So n is not, this number n is not in our list of all prime numbers. P is supposed to be the largest. And that's a contradiction. And now we get to write these three funny letters, quid erat demonstratum, therefore we have proved what we set out to prove. Any questions? So if you observe, we didn't actually sit at a computer and write down even a single prime number for this proof. It's a proof by pure thought. It's just an argument, it's just a discussion between you and me. I think everyone in this room is now convinced it can't be the case that there are finitely many prime numbers. They have to be infinite. Okay? Any questions? Alright. Well, once you ask about the primes themselves, you might be interested in patterns of primes. Mathematicians like patterns and like finding patterns. So anybody know what a twin prime is? Yes, back there? It's two primes that are two away from each other. Numbers p and p plus 2, which are both prime numbers. So let's just look at that list, that table that we had. So 3 and 5 differ by 2, and they're both prime numbers. 5 and 7 differ by 2. 11 and 13 differ by 2. 41 and 43 differ by 2. And this is the sequence of the first few pairs of twin prime numbers. What's the most natural question we would ask when we see a list like this? How many? How many, right? Are there 10, 30, a million? Are there infinitely many twin primes? Again, you write a computer program and ask it to give you lists. It gives you lists for as long as you like. But that's not a proof. That's not a rigorous argument that tells you what the answer has to be and always will be forever. So what's the answer? Anybody know? You're right. That's the correct answer. The correct answer is nobody knows. 2,300 years after Euclid's proof that there are infinitely many primes, the very next most natural question you could ask, patterns of twin primes, we still do not know the answer. We don't know the answer rigorously. We think we know the answer. We think it's yes. Well, why shouldn't there be? But that's not a proof. Mathematics requires nothing but absolute proof. Is that clear? All right. And no one has given one for this problem. Here's a little homework assignment for you. Why can't you use the argument we just gave? We just gave Euclid's argument that there have to be infinitely many primes. Try to adapt that argument to this problem. What goes wrong? Think about it. You don't have to give me an answer now. That's a homework. All right, here's another pattern of primes that people like. These are called Mersenne primes. Anybody know? Anybody heard of Mersenne primes? Anybody know what a Mersenne prime is? Okay. Okay, these also make the math news sometimes, but again, that's probably not your Sunday morning reading. It's named after this guy, Mersenne, who was studying them in the late early mid-1600s. A Mersenne prime is a prime number which is almost a perfect power of 2. So the powers of 2, 1, 2, 4, 8, 16, 32, and so on. A Mersenne prime is a prime number which is just one less than a power of 2. So let's just see. 2 to the 1 is 2, and if we subtract 1 off of that, we get 1. In Mersenne's time, 1 was a prime, but for us, 1 is not a prime. How about 2 squared? 4 minus 1, 3. 3 is prime. That's a Mersenne prime. That's our first Mersenne prime. 2 to the third is 8 minus 1, 7 is prime. 2 to the 4, 16 minus 1, 15 is 3 times 5, not prime. Okay, we can keep playing this game forever. 32 minus 1 is 31. This list is much more sparse than the last one, but here's a number. Anybody know what 2 to the 4, I can't even read, 43 million, 100 and whatever, minus 1. I'm not going to write it out because it's 10 million digits long. But this number is the largest Mersenne prime we know of today. Question? Oh no, just a stretch. Just a stretch. Stretches are allowed too. Of course, what's the natural question? Are there infinitely many? What do you think we know about this? Nothing. Okay? Let me tell you a little anecdote. There's a very famous lecture by a guy named Frank Nelson Cole. There he is there. In 1903, 110 years ago. What he did is, now imagine if I did this to you. He spent an hour, his entire hour lecture, he spent computing in utter silence on the blackboard. Just computing. What was he computing? Something very complicated? No. Well, it's something a little complicated, but it's nothing that you couldn't do on your own with 1,000 hours of paper and pen. He computed 2 to the power of 67. Well, subtracting 1 even I can do, but this is 2 to the 67 with an 8 there. That's a huge number and a huge computation, and it took him about a half hour to get all of the numbers down and do the long, you have to multiply it out in a clever way, not just the most trivial way. And he gets that number. That takes a half hour. On the other half of the blackboard, he writes down that number, 103 million, and so on. And he writes down that number, 700 billion. And he stands there, and in front of a room like this, of professional mathematicians, not 8th graders, he multiplies this out. And as he's nearing the end, you're hearing oohs and ahs as people realize that he has factored 2 to the 67 minus 1, which is not a Mersenne prime because it's not a prime. Okay? So, okay, on a computer today, you do this in a second, but I hope you appreciate the magnitude of difficulty of this problem, and that we really don't know very much about Mersenne primes. And much in the same way, when you get to very large prime numbers, twin primes are a bit mysterious. So let's get back to the Riemann hypothesis. This is the problem we're trying to understand today. What's the moral of the examples we just discussed? Prime numbers are very mysterious, and we know very little about them. Now, the Riemann hypothesis says 2 things about them. Number 1, it says that the prime numbers are beautifully structured. They have an amazing structure. And number 2 is that prime numbers are completely random. If it sounds like those 2 things are in direct contradistinction with each other, you'll see what I mean. So I have to explain exactly what these statements are. So let's start with number 2. Let me try to explain to you why primes are random. Okay? Here's a guy. Maybe you've heard of him, Mobius. He's named after this strip. Maybe the other way around. And what he did is he gave a spin to numbers. So 1 has spin up. It's 1. It's got to have spin up. 2 has spin down. 3 has spin down. What do you think the spin of 4 is? How many people say up? How many people say down? Well, it has no spin. You didn't know there was an option C. How about 5? Spin up or down?
Down.
Down. How about 6? Up. How about 7? Down. 8? No spin. 9, no spin. 10 is up. Here's the next 10. What's the pattern? Yeah, what's the connection? All right, let me pick on you again.
It looks like all the multiples of 4 have no spin.
What about 9? Yeah, we got one back there.
Squares have no spin and primes have a downspin.
12 is not a square. It has no spin. It's an excellent guess, though. Yeah, up.
All prime numbers are down.
Yes. So there are 4 rules. Rule 1 is that 1 has spin up. Rule 2 is that any prime number has spin down. What's rule 3? It's almost what you said. Whenever a number has a square divisor, whenever there are 2 prime factors of the same prime in a number, like 4, which has 2's in it, 8 and 9 are divisible by squares. 12 is divisible by 4, which is a square. Those spins cancel out, and that number has no spin. And what about a number that's a product of distinct prime factors? Well, each prime factor contributes a downspin, and 2 downspins cancel out. to an upspin. Okay? So let's just see if we understood what that means. Let's compute the spin of 30. So what do we need to know to compute a spin of something? We need its prime factorization. So what's the prime factorization? Oops. What's the prime factorization of 30? Pretend you're, yeah, 2, 3, and 5, good. So what's its spin? 2 gives it a spin down, 3 gives it a spin down, 5 gives it a spin down. 3 down spins is the same as 1 down spin. It's just the two down spins cancel out, so 30 has spin down. Okay, that's Mobius's function. Now, it's nicer to think of, instead of arrows, numbers, so let's just convert an up arrow into a +1, a down arrow into a -1, and no spin is 0. Okay? So here's Mobius's function again. If some square divides the number n, then you get 0. If n is a product of an odd number of distinct primes, then there's one spin that's not matched up. And if n is a product of an even number of prime factors, then it has spin +1, just as we just said. So let me just put the table there again. So here's the first line is just the numbers, the second line is their spin, as we just saw, and the third line is the Mobius function, which converts arrows to numbers. Any questions? Now, what are the partial sums of the Mobius function? So what do I mean by partial sums? You take some number x, and you add up the first x spins. Let me explain what that means. So let's start with x at most 10. So we start here at 0, and when we get to 1, 1 has spin +1, so we take a step up. And when we get to 2, 2 has spin down, it has Mobius -1, so we go down. What happens at 3? We go down. What happens at 4? Nothing. We just stay where we are. What happens at 5? Down. 6, up. 7, down. 8 and 9, we don't do anything. 10, we go up. You see what's going on? Let's go out to 20. So the first 10 is exactly what we just saw. And then 11 goes down. 12 doesn't do anything. 13 goes down. 14 goes up, and so on. Okay? You do it out to 100. And you do it out to 1,000. And you do it out to 20,000. Isn't that weird? Yes, it is weird. Thank you. Yes, thank you. This is what we mean by primes are random. Now, I have to explain what that means. So let me explain what I mean by a number being random. Well, what does it mean to be random? Say I have a 3-sided coin. I don't know how you get a 3-sided coin. But suppose it flips with probability a third and lands up, with probability a third it lands down, probability a third it lands, I don't know, on its side or something. If we were to add up these partial spins out to 20,000, here's one sample picture. Now in probability theory, there's a very famous theorem called the central limit theorem. I'm not going to prove it for you today. But basically what it says is, you should compare a curve like this to the graph y equals root x. Plus or minus. So there's this, it's a parabola y squared equals x. So it's just a parabola, but it's on its side. And what you should be seeing, what this theorem says is, this path should stay inside the curve. It's allowed to touch the curve. It's even allowed to go a little bit outside the curve. This is a very formal mathematical, that sounds like a wishy-washy statement. It's a formal mathematical statement, which I don't want to tell you because it's complicated. But that's the essence of what it says. You should compare this curve to the curve root x. And it should stay inside this bound. Let's see what's going on with the Mobius function. So let me put these Mobius sums that we saw. There it is. Can you even tell which path is which anymore?
Yes.
Yes? Some yes, some no. It's hard to tell. The Riemann hypothesis says you can't tell. It looks random. All right, let's just test this out. Anybody got a coin? Raise your hand if you have access to something you can flip. There are 3 of you with coins in here? Ask your mom. Okay, raise your hand if you have a coin. Anybody who's got a coin, if you have more than one coin, you can give it to your neighbor and hope they give it back to you. Okay, you have coins? Whoever has a coin, keep your hand up. Now we're talking. All right. Here's what we're going to do. We're all going to flip our coins. Okay? You flip, you catch, and you see what you have. All right? Everybody flipped? Now, once you know what you have, I have a heads. So just hold your hand up in the air. You're going to tell me one at a time what you have. We're going to go around the room. You're going to tell me what you have. Okay? Ready? Wait a second. Don't tell me yet. I'm not listening. Okay. I had a heads. Who's got a hand up? Please. Heads. Keep going as fast as you can. Heads. Tails. Tail. Tail. Head. So just keep going. Just yell it out. Tail.
Head.
Head.
Tails.
Tail.
Tails.
Tail.
Tails.
Tail.
Tails.
Head, I heard. Then I heard a tail.
Tails.
Head, and then a tail. 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 Tail, good. Head. Tail. Tail. Head. Am I making a mistake yet? No? Keep going.
Tail.
Tail. Head. Head.
Tail.
Tail.
Head.
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 Head. Oops. Head. Tail. Head.
Give me my coin back.
2 in the back. What do you got? Head? Over there? Tail? Alright, that should be enough. Let's see if this works. That's our graph. This is the sequence of heads and tails that you just yelled out at me. And as you see, look at this. We had about 40 people call things out. If every single one of you had a head, this graph would just go straight up to 40. The square root of 40 is like 36. The square root of 36 is about 6. And this is 6. And here's give or take 6. And look at our graph. Obviously, I couldn't have rigged this. That's what the central limit theorem says. And what the Riemann hypothesis says is that the sums of the Mobius function behave in exactly the same way. Let's go back. Let me try to explain it to you a little better. Whoops. Here we go. All right. Let's look at another version of this. There's another version. Well, for that we need to remember log. So what's log? It's not that. It's the logarithm function. Y equals log of x. So if you don't know what this is, you don't really need to know. It's the inverse function of e to the x. And if you don't know what that is, let me just remind you that e is a number between 2 and 3. It's called e after Euler, although it was known long before him. Here's a graph of 2 to the x and a graph of 3 to the x, and e is between 2 and 3, so it's just a curve that sits inside. And what does it mean to be the inverse? It means if we draw e to the x and we flip everything along the line y equals x, if we replace the role of x and y, we get this curve y equals log x. Okay? If you haven't seen this before, it doesn't really matter. It's just some function, gives you some number. Its value at 1 is 0, and there's another property of it that we'll need in a minute. So let me tell you what the von Mangold function is. I looked all over Google Images. I couldn't find a picture of von Mangold. Sorry. So here's what it gives you. For the number 1, it gives the value 0. For the number 2, it gives the value log of 2, which is like 0.69. For number 3, it gives the value log of 3. What do you think is the value for 4?
Log 7.
Log 7 is an interesting guess. Log 4 is a better guess. It's log of 2. How about 5?
Log 3.
Log 5. Okay, how about 6?
Log of 2. Log of 2.
0.
Hey, I get better.
You do? How about... Oh, I clicked too soon. Okay, what's 8 going to be?
Log of 2.
Log of 2. Good. How about 9?
Log of 3.
Log of 3. You got it. How about 10?
Log of 2. Log of 0.
0. All right. So I'm just writing out the numbers. So you see log of 3 is just 1.1. Log of 7 is 1.9. What's the pattern? Yes, sir.
So on the odd number of prime numbers that is factorized by, it is log of that number. When it's log of even, it's the 0.
Close. It's sort of what you said. You get log of a number if the number is an exact power of a prime. So for example, 8 is 2 cubed. So it's a power of the prime 2. And that's why you get a log of 2. And 9 is 3 squared, and that's why you see a log of 3. And 5 is 5 to the 1, which is why you see log of 5. And what about numbers that aren't powers of primes? Just put a 0. 6 is divisible by 2 different primes, you get 0. 10 is 2 times 5, you put a 0. Okay? Let's look at the partial sums of this von Mangold function. Here they are. Again, let's graph them out to 10. So what does this say? We start at the origin. We get to 1, we add 0, so we don't do anything. We get to 2, we add 0.69. We get to 3, we add 1.1. We get to 4, we add 0.6. We get to 5, we add log 5. We get to 6, we add nothing. We don't move, and so on. Okay? So it's this little step function like that. That's the partial sums of the von Mangold function. Out to 20, it looks like that. So again, the first half is what we just saw. Out to 100, it looks like that. And out to 1,000, it looks like that. What does that look like? It looks just like the graph of y equals x. Let me show you y equals x. Isn't that weird? Let's see, you see it's sort of wiggling around the line y equals x. Let's see what happens if we subtract off y equals x from that sum. So what do I mean by that? We're going to take these partial sums and subtract x off of them. So let's go out to 10 again. Here's the graph out to 10 that we just discussed. Here's the line y equals x. And we're going to take, at any point, we're going to take this number and subtract that number. So we get, at the first at least, we'll get negative numbers. So there's the difference. That's the wiggle that we're seeing. Here's that same wiggle. So you see this wiggle pattern out to 10. We're going to see that same wiggle pattern out to 10 here, but then we'll keep going out to 100. There's the wiggle pattern. And out to 1,000. There's the wiggle pattern. What does that look like? Random. It looks random. How do we test if it looks random? How do we test if it looks random? Yeah, let's test it against this parabola. There's the parabola. Well, you don't see it yet, but when you go out quite a bit further, it's going to start hitting the boundaries of the parabola. But it's supposed to stay more or less inside. It's supposed to behave just like a random function. Okay? So let's recap. The primes are random in 2 ways. We can look at partial sums of the Mobius function. That looks random. We can look at partial sums of the von Mangold function with this x subtracted off. That looks random. Is there a relationship between these two phenomena? So let me try to explain that. I'm running low on time. So remember, log of 1 was 0. And the only other property we need is if you multiply 2 numbers and take their log, it's the same as adding the values of the log. Here are the values of the von Mangold function, which come out of spins. I'm just reminding you. Here are the values of the Mobius function, and here are the values of the von Mangold function, and their, log of 2 is just some number, 0.69. Let's go back to our favorite number 6. What were its divisors?
2, 3.
1, 2, 3, and 6. Let's put von Mangold function of 6 on one side. And on the other side, let's take the Mobius function and multiply it by log and evaluate that at the divisors. So we'll put Mobius of 1 log of 1, Mobius of 2 log of 2, Mobius of 3 log of 3, and Mobius of 6 log of 6. And let's add all of these numbers up. Okay, so what's von Mangold of 6? Use your table. Of 6, von Mangold. Sorry, lambda of 6 is 0. Right? 0. How about Mobius of 1?
So 1.
Mobius of 1 is plus 1, but log of 1 is 0. Mobius of 2 is Mobius. So Mobius is the one with a mu, and maybe you don't know your Greek letter. Mobius is the top guy, and okay, so Mobius gives you a minus 1 times log 2. Mobius of 3 is minus 1 times log 3. And Mobius of 6 is plus 1 times log of 6. So let's just check. Here's 0, and here's 0. Somebody's already got it. Log of 6, by that formula, is log of 2 times plus log of 3. Here's a minus log of 2 and a minus log of 3. And what do you get? 0. They all cancel out. So here's another homework. Prove, give a rigorous argument that in complete generality, if you take a number n and you write all of its divisors, just like we did, d1, d2 up to dk, and you take the von Mangold function, and you take Mobius at the divisor times log of the divisor, you add this up over all the divisors, you will always get 0. Okay, excellent. So this is the relationship between the von Mangold function and the Mobius function. They're very intimately related to one another through this function log. Okay, let's recap again. The primes are supposed to be random. If you look at partial sums of Mobius or von Mangold minus x, they both stay inside this curve root x, and that's what it means to be random. That is the Riemann hypothesis. The Riemann hypothesis says primes are random. But Riemann, as I explained, saw something much, much deeper, and it's that primes are perfectly structured. In fact, he heard the music of the primes. So that's what I'm going to try to explain. Okay, so we have to talk a little bit about music, and for that, let me introduce you to a few friends of mine. This is Bess, Rose, and May. So this is Bess. Bess is an alto saxophone. This is not Bess's best day. I don't know if you guys can see up front, there's rubber bands all over it, because one of the posts came off this morning. Let's hope it's the worst. That's Bess. This is Rose. Say hi, Rose.
Hi, Rose.
Hi, Rose. Anybody know what that's called? Soprano sax, right?
Oh, it's right.
Rose. See if she's up and running. This is Rose. And May. Anybody know what May is? Clarinet, right. May is a clarinet. Been sitting around for a little while. Okay, so we have these three horns. An alto sax, a soprano sax, and a clarinet. So the saxophones were invented by Adolf Sax in the mid-50s. And I want to present you with three mysteries about these horns. So mystery one, let's measure the length of the soprano and the clarinet. So if you see, well, we have to unwind this. The soprano is a little wrapped up. But if we unwind it, you see they're about the same length. They're almost exactly the same length, these two horns. This one's wound up, so it's hard to see. That length is about 26 inches. You could even tell here. Yeah, 26, 27 inches. Okay? How about the alto? The alto is, if you were to unwind it, it's 39 to 40 inches. And does anyone notice a relationship between 39 and 26? What's the ratio from one to the other? 2/3, right? Or 26 times 3/2 is, so we can see that by comparing the clarinet to the sax, to the alto, and seeing that what's left over is about half of the clarinet. 1.5 the length of the clarinet is the length of the saxophone. All right. Why these lengths? Why is this ratio? What's so interesting about 3/2? Mystery one. Mystery two, let's study the lowest notes on each horn. So on the sax, on the alto, that's the lowest note. On our clarinet, that's the lowest note. They're pretty close, right? The lowest note there is almost exactly the same note as the lowest note on an alto. Alto just has one more half step lower than a clarinet. So the lowest note on May is almost the same as the lowest note on Bess. Falling apart over here. As opposed to Rose. That lowest note is much higher than the lowest note on the other guys. It's in fact 3 halves. I'll try to explain what that means. 3 halves higher. So, question 2, why does this happen? Question 3, the saxophone sound is often described as being lyrical and voice-like and very sort of warm. It has kind of a warm quality to it, whereas the clarinet is often described as having a very pure sound. It's a very I don't know, you can tell the timbres are completely different from a saxophone to a clarinet. So question 3 is, why are the timbres so different? So let's summarize our mysteries. As far as length goes, the alto sax is the odd man out. Rose and the soprano and clarinet have about the same length. But if you look at lowest note, the soprano sax is the odd man out. Soprano has a much higher lowest note than the alto or the clarinet. And as far as timbre is concerned, the 2 saxes have a warm sound and the clarinet has a pure sound. Clarinet's the odd man. So why are these things happening? Well, to understand that, we have to understand what is sound. So, I'm running very low on time. Let me try to rush through this. Sound is a mosh pit. You have a whole bunch of people in a room, they're all dancing, and if one of them, if one guy just shoves in a random direction, everybody nearby starts to fall and tumble. And if you're looking at this from overhead, you see regions where people are squished together and regions where there is little space. So sound is a mosh pit of air molecules. What's really going on is, as my voice tries to communicate with you, I'm squeezing air, and that air gets pulsed towards your ear, and you have an eardrum. On one side is just normal pressure inside your head. On the other side is normal pressure in the room. That gives silence. But when there's a disturbance, when the pressure is higher, your eardrum pushes in, and when the pressure is lower, your eardrum pushes out, because there's pressure on the other side. So that fluctuation of the eardrum is exactly what we hear as sound. So when you see a graph, it's a graph of the pressure. It's not that sound is going up and down. Sound is being pushed towards you and pulled, air is being pushed towards you and pulled away from you. Okay? So if you see, people have a misunderstanding of what, there's nothing going up and down. What's going up and down is the measure of pressure. Okay? So again, what do we hear? Let me explain what that is supposed to represent. You get it? So for a while there was no sound. All of a sudden there was a big change in pressure at your ear, and then there was no change in pressure again. So that's one clap. Now if we were to clap once per second, so that's called a 100 hertz, 1 hertz, it would look like this. Join me. Don't rush. Yeah. So that's 1 clap per second. The time between each clap, between each fluctuation is the period. 1 over the period is the frequency. How many claps per second? And as we already said, that's 1 hertz. Now what if we were to clap softly? What should the graph look like? Yeah, it's exactly the same difference in time, but the amplitude is changing. Instead of a big amplitude, a big change in pressure, it's a small change in pressure. We hear that as volume. So amplitude is volume. It's measured in decibels, which is 1/10 of an Alexander Graham Bell. The decibel. All right. What if we double time it? Right. That's 2 hertz. 2 beats per second, and the graph just has more wiggles. Let's try this. What if on one hand, you can do this on your knees maybe. On one hand, you clap regular time. On the other hand, you clap double time. You get it? What does the graph of that look like?
Same thing as that. Exactly.
There's a big beat and then a little beat, right? When both hands clap, you get a big beat, and then when only one hand claps, you get a little beat. That is exactly the sum of this picture and this picture. You see, if this goes up a height 1 and this also goes up a height 1, then the sum of the two go up a height of 2. And here it's 1 plus 0 is 1. Okay? Does everybody see that? So when you add two sounds on top of each other, that's the superposition of sound. The waves just add. How about 1 to 3? Yeah, not bad. How about 2 to 3? Not bad. Some of you are getting it. How about 4 to 3? Anybody? Some of you are really getting it. Let me give you a little harder one. 4 to 7. Practice. All right, so let's recap. What do we experience? There are beats and there's what we experience. What we hear is frequency, is how many beats a second, and amplitude is how strong is each fluctuation, how loud. So amplitude is volume. So if we were to sing this, what would it sound like? Let's try it all together. So we don't change the note. The period is still the same, but we just sing quietly, then loud, then quiet. Ready? Go. Yeah. Okay. That's amplitude as a wave. How about frequency? Frequency we hear is pitch. A fast frequency we hear is a high pitch, and a low frequency we hear a slow wave we hear as a low note, and a high note we hear as a fast frequency. So let's try to sing this. Ready? Okay, you get it. So frequency is pitch, and amplitude is volume. If we speed up that little clap that we were doing, not twice per second, not 3 times, not 100 times, 440 times a second, what we would hear is, that's an A440. The reed is fluctuating 440 times a second, and that fluctuation is making its way to you. Your brain interprets it as sound. That's an A. What if we were doubling to double that frequency, not from 400 to 880? You would hear just 1 octave up. Okay? So changes in frequency correspond to changes in the note. What about timbre? What about quality of sound? How do we understand that? Yes, somebody said it. Okay, if I play the same amplitude and the same volume, same amplitude, on both notes, they still sound different. Same frequency, same amplitude. What's different is the shape. The quality of the sound is determined by wave shape. So you could have a wave that looks like these triangles, these heartbeats, or you could have a square-looking wave or one of these sinusoidal waves. They sound different even if they have the same frequency and amplitude. And how do we understand this? Through calculus, which obviously I'm not going to go into, but it's work of Joseph Fourier, who showed that any wave whatsoever can actually be decomposed as a superposition, just as we saw before, of very simple pure waves. So you just have to use the right frequencies and amplitudes. Let me try to explain. So let's decompose this 2 on one side and 1 on the other side. Let's decompose that beat into pure waves. So These are waves that are going around at 1 hertz. This is a sine wave. It's barely fluctuating at all. Very small amplitude. Here's at 2 hertz. It's wiggling twice as fast. There's at 3 hertz and 4 hertz. So you see the amplitudes are different, and the frequencies are integer multiples of the original frequency. So this is wiggling at 4 beats a second, and so on. Here's the 10th contribution. And if we superimpose the waves, if we just add them on top of each other, when we go up to 5 hertz, this is what the superposition looks like. I don't know if you can tell the heartbeat underneath the superposition. And if we go out to 10 hertz, that's Fourier's theorem. The theorem is you just take these very simple waves and you add them up and you can get any wave you want. And that is why you can play Riemann on your iPod. Is because all the computer can do, computers can't store complicated waves like this. They can store numbers. All the computer has to do is store the frequency and the amplitude of a bunch of numbers, and then it can make any shape of wave whatsoever. So let's solve our 3 mysteries. Here they are again. Saxophone is the odd man out, the alto is the odd man out. Likewise, as far as the low note, the soprano is the odd man out, and as far as timbre, the clarinet is the weirdo. So let's answer the timbre question. The sound, again, is determined by the resonant waves. The clarinet is a cylinder. The length of the circle here is almost exactly the same as the length here. It just looks like a straight cylinder across. Everybody see that? Whereas a saxophone looks like a cone. It starts out very, very small and gradually gets bigger. Never mind the twists. Gradually it gets bigger and bigger. So it looks like a cone. And so the fluctuations, the fact that the clarinet has a cylindrical bore means its overtone frequency doesn't have even multiples. If I overblow, you're supposed to, if I play all of the multiples of the original wave, so that's the actual full overtone series. Now, if I don't change my fingers at all, and I just put more energy, it's like jumping from an S valence to P valence electron, you'll hear it. It's skipping every other note that it should be playing. That's what you should be hearing, is instead what you're hearing. Okay? And that is just by changing how much pressure I put, how much power I put through the horn. A saxophone has a conical bore, as we just said, and that allows you to overblow all harmonics. Now, the wave isn't a simple sine wave. It's a little more complicated. It's actually sine x over x. But it allows all frequencies to overblow. And you should hear... I hope she's okay. Okay? You heard almost all the harmonics. I'm sorry she's having a bad day. But the point is you're hearing the full overtone series on a sax, which you don't hear on a clarinet. So the answer to question 2, why is the lowest note different? It's the same answer. It's the physics, it's the mathematics of what notes are the resonant waves going into Fourier's theory. And it's just a fact from calculus that if you have a cylindrical bore, a bore that looks like a cylinder, it resonates at 3/4 the length. It resonates the same frequency as a cone, which is 3 times as long. So 3 halves times as long. So even though the alto is quite a bit longer than the clarinet, they have the same lowest note. Whereas the soprano, as expected, has a higher lowest note because it's shorter than the alto. How about question 1? Same answer. We just gave the answer. The lengths are different because these are the frequencies going into the horn. So all of the mysteries are solved by understanding the resonant waves, the resonant frequencies. Math explains everything. So let me give you 3 homework problems. Here's some things to explain. What's going on if we pop a note? What's going on with that pop? Here's another phenomenon to understand. How about multiphonics? What's happening happening there? That was weird, right? And the third one, what happens? We've only been discussing single notes, but of course music is about not just single notes. Music is about harmony, notes playing together. Give me 1 second. What's harmony? It's several voices playing at once.
How do you do that?
What's going on in your ear there? Let me give you a hint. Remember when we were clapping 2 to 3? Think about it. All right. Let's get back to the Riemann hypothesis. What was the Riemann hypothesis? I don't even remember it anymore. What Riemann actually proved is a mathematical theorem that he proved, and that theorem is basically the analog of Fourier's theorem. He discovered some amazing ways. I'm over time. Just 4 more minutes of your time, if that's okay. These are some of the waves that Riemann discovered. And if you look at their superposition, if you just add all of these waves up, you get something that looks like this. Does that look familiar? It's the... We already saw this curve. It was the wave that we got by subtracting off x from the sum of the Von Mangel. Let's go back. Let's go back to the very beginning. In the very top, recall the Von Mangel function. It has these log values, and it tells us which numbers are prime. 4 prime powers, but there are very few prime powers. So the prime numbers are the ones that are contributing the most to that. And we looked at its partial sums, and we saw a picture like this. And we immediately, so the jumps tell you where you find primes, or prime powers. And we immediately observe that there's this, the graph just looks like y to the x. Y equals x, right? That, what we saw with our eyes, there it is the fundamental frequency of the primes. It's the main frequency. It's the one that tells you what note the primes are playing. But to get the full characteristic, it's the one that sounds the loudest. To get the full characteristic, you need the superposition of all the harmonic waves. That's Riemann's theorem. So let's just add this first wave. Remember this wave 1 that I showed you, Riemann's wave 1? Let's add it on top. Everybody see what happened? Let's go back. We were there. That's y equals x. We added on top. It's better approximating that step function. Let's add a second wave. Here's wave 2 on top of, we already added wave 1. There it is. How about going out to wave 10? You get that. How about going out to wave 100? Wow. You see? It's getting closer and closer to exactly matching that step function. So that's what Riemann proved. That there are these beautiful pure waves, just like in Fourier's case, they're determined by 2 numbers. Any wave has 2 numbers. What 2 numbers? What do you need to specify? Frequency and amplitude. How fast to wiggle and how loud to play. And what Riemann did is he plotted the frequencies and the amplitude. Wave 0, that fundamental, that y equals x line, has frequency 0. It's not wiggling at all. And amplitude 1, it's sounding the loudest of all. All of the other waves, they have some frequencies, which we don't know, you can compute what these numbers are. And they have all of their amplitudes playing at exactly volume 1/2. That 1/2 is the same 1/2 as the line y equals x to the 1/2 that we saw in the randomness. So what do you think the Riemann hypothesis states? Looking at this picture, what should we conjecture? Where do you think wave 11 is going to be? Over here? Over there? Over there? Over there? Yeah. The Riemann hypothesis says all of the waves that add up play at exactly the same volume. There's a perfect harmony. This is the perfect structure of the prime numbers. All of the waves, the music that's making up the primes, there's this very clear line y equals x, and everything else is contributing much, much less, and the amount is exactly by half. That's the perfect structure in Riemann's theorem. All right. let me just say I stole these pictures from Wikipedia and Google Images. You should also check out this wonderful book by Marcus de Soto called The Music of the Primes. And eventually I'll throw some of these pictures and computer programs on my website so you can download them there.